So welcome everyone. Welcome everyone online as well as here in Cambridge. We're counting that now to the 57th Cheminformatics meeting. Can you hear us online as well? Yeah, is that okay?
Yeah, good.
Yes.
Okay.
Yes.
Thank you. Okay, so first, and that only applies locally, fire safety. So if there's a fire, there are the green signs. We follow those and meet outside for some fresh air. And so, as usual, the aim is to bring everyone interested in cheminformatics together, discuss interesting topics in the widest sense relating to that topic. So this time it's about 280 people or so registered. Of course, not everyone turns up, but it's a good audience, I think. And I think this time I'm actually quite impressed, and that deserves a special mention. I think we have a visitor who came over from Japan for our Cambridge Cheminformatics meeting, Buncho. Yeah. So please have a chat with Buncho in the pub. Yeah, he came all the way from Tokyo. Much appreciated. So we'll have 3 talks as usual, and afterwards go to the Penton Arms. And we just fixed the dates for next year as well. So they're on the website too. 19th of February, then in April, September, and in November. So it's a similar schedule as this year. So please do join us next year as well. It will be hybrid mode again. So very welcome to join here or online. And as last time, thanks to the RSC, as well as Rigid Seal, who got a grant for some nice food today, and to Emily Clark from the CCDC as well for organizing that for us. We will record the main meeting. I will coordinate then with the speakers what can be put online. So there's the YouTube Cheminformatics channel. So check that afterwards, linked from the same website for the recordings that we're able to share. For questions, so online, please feel free to type them, and then we will go through the online questions as well as the local ones. And after the last talk, so please stay online. So locally, we go to the Penton Arms, as well as online, we will put people into breakout rooms so you can meet some cheminformatics people that you might know or might not yet know. And if you wish to present, so it's open to all, please just send me an email and everyone is welcome to do that. Okay, and so this is the agenda for today. So we will go from startup companies. Jinhan Kim from Standigm is joining us today, who will share his experience, how he started Standigm, so one of the leading Korean AI and drug discovery companies. We will go to a topic that's actually quite close to my heart, molecular similarity. It's a topic I worked on in my PhD as well. So Marcello will present on that. And afterwards, we will have a local talk from the CCDC, Nicolas Francia, who will tell us about comparing crystal structures and analyzing large sets of theoretically predicted structures.
Hello, everybody. Today I'm going to talk about some of my work that I've done during my PhD in chemical similarity, and I will present Hypershape recognition, a general framework for moment-based molecular similarity. So, similarity is a widely adopted concept in chemistry and cheminformatics. And its utility stems from the similarity property principle, which states that similar chemical entities are likely to display similar properties. And this allows us to avoid long experiments or costly computation and just compare the molecules to some others that have some desired characteristics. And this principle is particularly useful in medicinal chemistry, and it is for this reason that the majority of the similarity measures have been developed in the field of drug design and discovery. And although there are other applications, the point remains that most of them are suitable for organic compounds. And they face some challenges when they are applied in a different system that contain metals and or show bonds that are not described by standard balance rules. So for these reasons, to our knowledge, no similarity method tailored for inorganic and organometallic molecules have been reported. And the development of a general similarity to handle both organic and inorganic molecules is the object of this work. So in order to construct a new similarity method, one of the first steps that we need to do is to choose what representation to use. And there are many, but they can be broadly divided based on the dimensional information that they have. But working with inorganic molecules limits this choice severely. And this is because there is no widely adopted definition for bonds that are particular for these compounds, like dative bonds, multi-apto bonds, for example. And also, there is not yet a consistent and standard topological representation of these molecules. So we have to rule out the 1D and 2D, and we have to opt for the 3D representation and 3D similarity. 3D similarity methods can be divided in two main categories: alignment-based methods, where the similarity is a degree of alignment between two molecules, and moment-based methods, where instead the molecules are first translated, or better compressed, into numerical vectors, which are then the objects of the comparison. Alignment-based methods allow us to compare, of course, shape, but also some chemical information to some degree. But since the alignment process is an optimization problem, as the molecules get bigger and more complex, their scoring can get slower. And instead, in moment-based methods, we can compare shape and molecular information and chemical information, although with some limitation, as we will see in a few moments. But since the comparison is between numerical objects, they are very, very fast. And for this reason, we decided to focus our attention on these methods and use this logic to base our method on. So how do they work? The prime example, and actually the first one to introduce their logic, is called ultra-fast shape recognition, and starts from the 3D representation of a molecule, and from its coordinates, it identifies 4 reference points in a heuristic way, like the geometrical center, the atom closest to the center, the atom farthest from it, and so on. And from each reference point, it measures the distances to all the atoms in the molecule. And so we obtain 4 distance distribution, 1 for each reference point. And for each of these distribution, we compute the first 3 statistical moments: the mean, the variance, and the skewness, hence moment-based method. And then their values are collected into a 12-element fingerprint, and these fingerprints are then the object being compared by means of this formula, which is inverse Manhattan distance, to give a similarity score between 0 and 1, which is the usual range a similarity measure is provided. This method is very robust and extremely fast, or ultra fast. The problem is that it is blind to chemical information, as it considers molecule like clouds of points in 3D space. So here are 2 examples of methods that built upon USR to introduce this information with different strategies. The first one is USR with Credo atom types, or USR cut, which applies the USR logic to the whole molecule, but also iterates it through a subset of atoms based on the atom types. And so the moments of all these subsets are collected into a 60-element fingerprint, which is then compared in the same fashion as we saw for USR. And instead, electroshape is another method which includes chemical information by adding atomic properties as extra dimension to the 3D representation. And by each dimension that we had an extra reference point and 3 moments to the fingerprint. So for example, in a 4D implementation of this method, where they had partial charge as an extra feature, we have fingerprints of 15 elements long. Although this method successfully introduced chemical information, it is still information tailored for drug design, which it's not always that useful if you want to compare inorganic and organometallic molecules. And also, all the implementation that are available in several software packages, they have not been developed for to be easily customizable, which is a property that we wanted to have in our method to make it as general as possible. So for example, it's not so easy to change the definition of the atom types, or if we want to add another property to Electroshape, we also have to come up with a strategy to identify the extra reference point and other complications. So with these concerns in mind, we developed our method, which we called Hypershape recognition. And HSR mostly follows a similar workflow to many other moment-based methods, with a unique and distinctive addition of a step that we call Hypershape. And the workflow has different customizable parameters, so that make it a framework, but it also comes with a default set of fixed parameters, which make it the HSR method. And this is actually the general purpose similarity that can be, in principle, applicable to any chemical system. So I will now go into some details of how this method works, and I will try to highlight what are the customizable part and what are the choices that we made for the method. So the first step is very similar to the one that I just showed you for the Electroshape method. So the chemical information is added as atomic feature in extra dimension. But differently from Electroshape, HSR can accept any number of these features as long as they produce a numerical value. And this is arguably the most important customizable aspect of the method, since it allows the user to introduce whatever information they want to focus on. And since the method that we wanted to have as a default aimed for generality, we had 3 extra features, the most fundamental that we could think of. So based on information about protons, neutrons, and electrons. And in particular, we have these 3 functions. The square root of the proton count. Here, delta n is the difference of the number of neutrons of the atom and the number of neutrons of the most common isotope of that element, also under square root. And the electron information is given as the formal charge. And here I want to stress that these scaling, these tapering function are completely arbitrary. And we end up choosing those for the default just because during our work we saw that they provided the most reasonable results for a wide spectrum of comparisons. The next step is actually the core of the method, which is the Hypershape and its manipulation. So once we obtain the n-dimensional representation of the molecule, we perform a principal component analysis, which adds some extra computational cost to the method, but also provides several benefits. First, it produces a deterministic orientation of the molecule. So independent from the original orientation, the same molecule will always be described with the same coordinates. Second, the presence of the principal components offer a very easy and deterministic way to define the reference points, one in the center and one for each component. And lastly, and most importantly, this offers a neat way to detect chirality and distinguish enantiomers. But I will go into detail about that in a few slides. So here the customization is actually to decide to switch on and off the chirality detection and to choose the position of the reference point. And the default method has the chirality detection off, and the reference points are positioned at the largest coordinate in that dimension. And this means that they lie on the surface of the hypershape volume. So they are well distributed around the molecule. And from here on, actually, the HSR method is the same as many others. So once we identify the reference point, we obtain the distance distribution, we calculate the statistical moments, and we collect them into the fingerprint. And in the default method, we actually use the same similarity score. Here we just add the possibility for the user to also get the raw distance, the raw Manhattan distance, if the user wants to manipulate it in different ways. So now that I described how the method works, I would like to show you results from some analysis that we conduct to test the behavior of both of the framework and the method. So the first result is based on the directory of useful decoys, and this test is meant to assess the performance of the HSR framework to emulate previous methods and replicate their results. I won't go into details of what the experiment actually is, but suffice to say that this has been a very common practice in presenting new moment-based methods, because it is a measure of how a similarity is good in identifying active molecules in a batch where decoys are present, meaning similar but inactive molecules. So the highest is the result, which is called enrichment factor. The better the similarity is in identifying the active molecules. But what we are really interested here is to see how close the HSR score in a given configuration is to the the original method. And we compare that result with ones that we found in the literature and some that we produced with current implementations. And from these data, we can see that HSR does indeed replicate the result quite well. In the first case, in USR case, actually produces the highest enrichment factor. USR cut is also very, very consistent. And the only outlier here is the Electroshape case, which actually did expected, since Electroshape, and in particular the scaling factor of the feature with the partial charge in the Electroshape was actually optimized for this specific experiment. And we did not perform the same optimization. So the next result is instead to showcase the capability of the HSR method to compare inorganic molecules. And to do that, we have some example, and we compare these results with USR and USR cut. And if we look at these results, we can see that USR, so ultrafast shape recognition, it can be applied to this molecule, but since it does not have any chemical information, when the change is very subtle, like in the first example, the result is its sensitivity is very low. And actually that sensitivity, a sensitivity this low makes it kind of impossible to distinguish if that signal comes from the actual change in the feature or some noise in the coordinates. And instead, USR cut has another issue, which is the fact that the definition of the atom types depends on the connectivity of a molecule. And so in cases where the connectivity, it doesn't change between the two molecules, like for example, in the second case, the results of USR cut are generally reliable. But in cases where the connectivity changes, so the atom types are no longer compatible, the USR cut similarity is not reliable anymore. So in the field of inorganic chemistry, where we don't have a unique connectivity, sometimes we could end up with the extreme case that we are comparing the same molecule with itself, but the two molecules have a different connectivity definition, and the similarity gets lower than 1. So not correct. So, and instead, HSR for these examples and in general for inorganic molecules does provide good and reliable results. As I mentioned before, one capability of HSR is the detection of chirality. But as I described it so far, if we were to apply it to a couple of enantiomers, in this case, 2 helicins, for example, we see that the score is 1. So the two molecules are not distinguished. They are the same. But we can notice that the two reference systems, which are the eigenvectors provided by the principal component analysis, by the PCA, are one left-handed and one right-handed. So they are also mirror images of each other. And this handedness, this property that can only be applicable in 3D, is actually extendable in multiple dimensions by looking at the determinant of these eigenvectors. So that is easily computable as the product of the diagonal of this matrix. So we will have -1 and +1 in the other case. And we can also see that this focus on the determinant can be applied to any dimension. And having noticed that, the chirality detection does work by imposing a sign of a determinant by simply change the orientation of one of the eigenvectors. And these results in a change of one of the reference points and ultimately a lowering of the similarity. So the two enantiomers are distinguished. And here are some examples at the top of organic enantiomers and the HSR value in a 3D scheme, so without any feature. And instead, in the last case, I put an inorganic case of optical isomerism. And here I provided the measure for both the 3D and the 6D. And this is because HSR is not the first method able to detect chirality, but is the first method that uses this strategy to do it. And it's the first one that can apply this detection safely in multiple dimensions. And as a last result, I want to show you this a very simple experiment where we just compared one molecule with an exact copy of itself, and we just switch one hydrogen with deuterium. And then we did this comparison for all the hydrogen in the molecule, and we can see that the similarities of this comparison are not all equals, but they actually fall into a range, a narrow range, but a range still. And this means that the effect of a change does depend on where it occurs in the molecule. And actually, it also depends on the size of the molecule, the shape of the molecule, and the nature of the change itself. And this is a visual way to actually highlight some characteristic and some limitation, if you want, of these methods. Because all moment-based methods, and HSR included, in the process of transforming the molecule into a fingerprint, lose some information. And this, of course, results in a great deal of speed for these methods, but also introduces some behaviors that are not easily predictable and sometimes change from comparison, from one comparison to another. And it's important to be aware of these characteristics. And also, as a very last comment, I just want to stress that similarity is a very subjective concept, and trying to put a rigorous number to it will always fall short in having a holistic comparison that satisfies all chemists. And this is because every chemist has their own background and their own interest, and their own biases also. But this actually is one of the main reasons that we decided that HSR is not just a method, but we made it in a form of framework, and we tried to make it as easy as possible to for the user to introduce whatever information they want to focus their similarity on. And as I mentioned, the HSR comes also with a method that for his fundamental properties can be applied in any chemical system. HSR is open source. It's available on GitHub and distributed as a Python package. And let me just conclude by say thank you to the University of Bergen, the Norwegian Council of Research, and the High Value Project for funding this research. I want to thank my supervisor and my group for the support, and I want to thank you very much for listening.
Thanks a lot, Marcello. And there's one comment online, Francois, if you want to say that, your comment.
Yeah, so in the beginning of the presentation, he was not mentioning that there are some molecular descriptors made by physicists, which are very generic.
Yes.
So the SOAP molecular descriptors, for example, they should be able to describe any molecule,
Yes.
as long as it is a point set in 3D, and the atom types are just chemical elements.
Yes. Of course, there are. In fact, what my statement is that there are general, and actually the USR method, the first one in this moment-based category, is actually very, very general, but they are not tailored for inorganic and organometallic molecules.
Okay, so the SOAP descriptor, it's an atom-centered environment. So it's not at the molecule level, but of course you can describe at the molecular level by kind of concatenating all the atom environment of a molecule. But a nice presentation, interesting. Thank you.
Thank you.
Yeah, just look that one up. What I found personally interesting when I was doing my PhD on similarity is how many concepts come from psychology. let's say similarity coefficients, asymmetric similarity coefficients. Yeah. Amos Tversky, he was a psychologist. He wrote quite a lot about human perceptions of similarity.
Yes.
Yeah. And those articles I found quite interesting to read in
Yeah.
the old times.
Yeah.
If you want to look up some more.
And yeah, and there is actually the effort to match the similarity to that with AI actually, to train models based on the actual answer from chemists.
Yeah, yeah.
So,
Yeah, that's one way, or you define explicitly how you define similarity, and then it is what you define, right?
Yes,
I mean, there's different
yes,
ways to do that. Yeah.
Yes, yes.
Any other? Yeah, no, please. Yeah. Wait one second. Okay.
Thanks, yeah, nice talk. One point I want to make is, or say that was very nice, was your final slide where you showed the effects of changing the atom at the Hypershape. It was very nice way of showing that it changes a different molecule, have different effects in similarity. I haven't seen that sort of diagram before. Clear way of showing that.
Thanks.
You made the point at the start that most similarity methods have been used in drug discovery similar molecules to request the project. What's the motivation for the work you're doing in your field?
My group has developed, actually, I have a slide for that. Has developed this method called the Noptim, which is a genetic algorithm for generating molecules in 3D, especially from fragments. And my group focus principally on homogeneous transition metal catalyst. So it is tailored for deal with organometallic molecules. And since in the last years, there have been many other models for this specific environment, for attack metal-containing molecules, inorganic molecules. We lack a benchmark for these methods. And so my goal, actually the work that I'm doing right now, is to create a benchmark for that. And to do that, I need an objective function, a fitness function that is quite good in detecting structural information of these compounds, so that I can tailor the targets to have given some properties that I want to benchmark for. And it has also to be quite fast, since the benchmark has to be run in a reasonable amount of time. Sorry.
Okay. And I think
there is one.
okay, yeah,
Sorry.
swift one, because I think afterwards we still have one more talk. Yeah, please. Yeah.
It's just a quick question. You can talk. Just a quick question about the PCA transformation at the beginning.
Yes.
I'm not sure how many times this occurs or if you've observed this, but what happens if a molecule has two principal components with very similar eigenvalues? For example, maybe if you just move an atom slightly, the principal components switch from 1 to 2 or 2 to 3. I don't know if you.
Yes.
Can you just repeat the question for the people online?
The question is if the PCA has some issue when there are dimensions that are really close in variance, so they can change quite rapidly. The short answer is yes, but the longest answer is the PCA is much better in handling these they are called discontinuity problems, so that a small change in the molecule will result in a big change in similarity. And by doing the PCA, you have these problems sometimes, especially if the change affects the surface of the shape, because the reference point moves quite a bit. But actually, with the PCA, this problem is much more mitigated than instead using the heuristic way of taking the closest atom or the farthest atom, but because In that case, there are many more possibility of having atoms at the same distance or very, very close. And so yes, it still has this drawback, but much less than previous method.
Okay, great. I think let's thank Marcello again. Thanks a lot.
Thank you so much.
You know how to find this letter? Let's see. CCN. No. Do you know where your slides are? How to is it in PowerPoint? Yeah.
Yeah, I think it's PowerPoint.
Do you know where you put the last slide deck? Whether it is on the desktop? Yeah, they're in the middle. This is. Okay, great, thanks. And we'll come to a local concluding presentation by Nicholas on comparing crystal structures. Yeah, Nicholas.
Yeah. Thank you. Hello, everyone. So in this presentation, I will talk about the application of crystal structure similarity algorithms with a particular focus on crystal structure prediction. So we'll show initially what the crystal structure prediction problem is, why it is important, and then a few challenges that we have found while analyzing a large set of structures. Starting from the very beginning, polymorphism is the ability of a molecule to adopt different packings. And this is very important because the properties of a crystal structure depends on the solid form. So if you're from a pharmaceutical background, you're particularly interested in solubility and dissolution rate because it affects the bioavailability. From the functional materials part, you are more interested in seeing how electronic magnetic properties might change from polymorph to polymorph. And a nice example of how polymorphism can affect a pharmaceutical company is the case of ritonavir that happened in the late 90s, in which this antiviral compound was initially put into market because a single form was known. But after a while, a second form, which considerably lower solubility, emerges dominant. And so the drug has to be withdrawn from the market with a lot of discomfort for the patients and the losses for the company. This has kind of a different effects, one of which was to use extensive polymer screening in searching for a possible polymorph given a single molecule, but also put a lot of attention on theoretical methods able to predict the crystal form starting from the diagram of a single molecule. Ideally, we would like to have something that directly goes from the molecule to the crystal structure. What happens in practice is that we identify a myriad of different crystal structures. Every point in this plot is a single crystal, and then we rank them with some specific energy model. In this case, for ibuprofen, we can see that form 1, which is the most stable, is also the global minima. So this gives certain that there won't be a late appearing of another polymorph in the tablet, for example. But this is not always the case. This is another example for olanzapine, for which initially only 2 forms were known, form 1 and form 2. But crystal structure prediction methods identify a series of other possible packings that weren't found experimentally. And what is interesting about this case is that the global minima, which is the blue dot on the bottom, was actually found a few years after the CSP study was published. Another important application of CSP methods is the comparison with, for example, pulpy-exterior patterns. So if you're not able to solve your crystal, identify it because of various reasons, you can have like concomitant crystal or something else. You can use the theoretical patterns obtained from CSP or a combination of them to try to make sense of your pattern. Now, as I said in the beginning, crystal structure prediction generates a lot of structures. The reason for that is because the search space is basically infinite. We have now a series of different algorithms that are able to guide search for the crystal structures, but still we know that in the end, a large number of structures are generated, and this increases dramatically with the number of molecules in the acid metric unit and the flexibility of the molecule, meaning how many conformers should we consider for the search. For this reason, the energy evaluation of the different crystal structures is done using a multi-step approach. You usually start with something that is very cheap, like a classical force field or something like that. Identify the low energy structure, apply an energy cutoff to eliminate a large amount of high energy structures, and then you increase your level of theory. So in the end, you basically go to very expensive methods, like, for example, dispersed corrected DFT, so quantum mechanical methods, to identify which of the different structures are effectively stable. In here, there is a first application of crystal structure similarity algorithm, meaning that since this method, especially in the last steps, are very expensive, we want to eliminate possible duplicates from our set. So we need something that is fast and it's able to remove duplicates and avoid performing the same simulation twice. A second, more obvious application of structure similarity algorithm is that once you have a final set and you're happy with it, you want to know if experimental structure are effectively being generated by your method. You want to be able to locate them and see if there are similarities between one another. Within the CCDC, we periodically organize a blind test on crystal structure prediction. And the last one, papers just came out a few weeks ago. We proposed 7 different systems. We gave basically a diagram to the different participants and asked them to predict which of the which crystal structure they could crystallize into. This came out as 2 different papers. The first one focused basically on the generation method, meaning we asked the participant to give 1,500 different structures and verify if the experimental structure were among those submitted by the participants. And the second one instead was related to the ranking of the different structures. So what are the relative stability between polymorphs? Are there other structures within the CSP set that have lower energies? Now, I won't talk about the general results of the blind test. There is a really nice presentation by Dr. Lini Anisat that I gave a few weeks ago. In this presentation, we focus on structure similarity algorithms and particularly on the first part. The reason for that is because we had a lot of participants to this blind test. So we had a base of 100,000 different crystal structure, and we wanted to test different crystal structure similarity method on this large set of structures. The first one that we look into is the one that's been traditionally used, is the crystal packing similarity tool that is based on the compact algorithm from 2005. And basically, it is based on taking one molecule from the asymmetric unity of the crystal, construct a molecular shell around it, do the same for a second structure, and then compare these two molecular shells. The output of this kind of analysis is basically how many molecules in the molecular shell are roughly in the same position, and among those that are in the same position, what is the RMSD between them. Obviously, we are interested in looking at very similar crystals, so those that have all the molecules in the same position. But it could be also interesting to look at partial matches, because we can identify, for example, systems that have similar layers or even two molecules that are connected together, so they form dimers that are the same. A second method that we have a look at is, and that one too has been traditionally used, is the comparison of PXRD patterns. This is basically done by generating a theoretical pattern from the structure from CSP and compare those theoretical patterns and giving a result between 1, meaning the two patterns are identical, and 0, that they are completely different. Finally, the third method that we look at was the point-one distance distribution. This has been instead recently developed in the University of Liverpool by Dan Widdowson and Vitaly Kurlin. And it's a method that kind of takes a different approach. It completely ignores the chemistry inside the unit cell. It just look at all the atoms within the unit cell, and then for each one of them create a distance vector from that reference atom and the nth nearest atoms. The output is a two-dimensional matrix in which each row corresponds to a single atom in the unit cell, but then goes one step further, meaning that those atoms that have the same set of distances are collapsed into a single row, and a weight is assigned to those systems. This creates basically a matrix that represents the symmetric unit of the unit cell, and that can be then compared between other crystals, between other fingerprints, using the Earth mover distance. Now, I will talk a little bit about the challenges that we found in most of the cases, also how we handle those challenges and improve this algorithm. The first one is strictly specific to the crystal packing similarity tool, so the first one that I showed before. This algorithm needs every atom in a molecule from a crystal to be mapped to the molecule from another crystal. So, for example, go here. Sorry. Okay. So, for example, the carbon in here needs to be mapped to one of the carbons in here. But since the connectivity between those atoms is the same, the system by itself doesn't know if the map should be with this other atom of this other atom. And this is a simple case. The way it was solved in the beginning was to look at all possible permutations. And here it's not a big problem, but molecule 27 from the blind test has more than 4,000 different possible permutations. So we updated the algorithm to introduce a sort of distance constraints in there, so that only the most plausible mapping between atoms are considered. In doing that, we were able to basically dramatically reduce the time needed to compare crystal structures. In the case of molecule 27, this was 30,000 times faster, so it was a big improvement that happen for topological molecules with topological symmetries. Another important thing to consider is basically the operating condition, meaning that somehow the definition of a polymorph is a bit ambiguous because we consider some types of distortion that are more important with respect to other. In particular, if we observe something like a thermal expansion, so we look at a structure at low temperature and high temperature and see that this increases, but there are no significant change in the rest of the packing. That is still the same crystal structures. Instead, if we have a change, for example, in the conformation of the molecule, that will resume in a different polymorph. This is particularly important for crystal structure prediction because, especially in the last test, we had a mixture of different methods. Some of them basically are considered CSP0, meaning they were done at 0 Kelvin without considering at all thermal effects. Other ones introduced thermal effects. But even so, when you are comparing structure at 0 Kelvin with what you find experimentally, for example, room temperature, you need to have something that accounts for possible thermal expansion. This is actually something that is well known from the comparison of PXRT pattern, because when you are changing the dimension of the cell, you obtain a shift in the peaks. There are different methods that are available to compare structures in these situations. In the case of the 7-blind test, we used the variable cell powder different method that was developed by the group of Erin Johnson, in particular by Alex Mayer. But there are other methods like the autofidel approach, for example. And the basic thing about these methods is that they consider one crystal as the reference one and try to adapt the other crystal so to match the reference structure. This example, you have in black the experimental form of molecule 29, and in red one theoretical structure. After applying the variable cell powder different methods, there is a slight change in the cell parameters, and right now it is basically the blue line, which, however, I don't know if you can see that because it's almost perfectly overlaps with the black one. Sorry. This is well known for the PXRD comparison, but the PDD method being entirely based on atom-atom distance has the same problem. So we basically added one step when comparing structure with the PDD method. One other thing that we wanted to look at was how close the landscape, the regenerated landscape by the different participants were as a whole. And the reason for that is because there were very few searches in the past that look at a few systems and different methods producing CSP landscapes, and find out that even if they found maybe the experimental structure, the metastable ones were strongly different one from the other. So there were little or no overlap between different CSP methods. And obviously this is not good because it means that there is something wrong with the generation, meaning it didn't converge, or with the ranking method, meaning it left out structure that were instead important. So to do that, we looked basically at given the fact that we had really a lot of structure to consider, we looked at the speed of every different methods. The PDD invariants had some false positives when we used them, but were by far the most, the fastest ones. So we basically used them to analyze the different landscape and see if there were similarities between them. And quite encouraging when we had to deal with relatively small molecules, not particularly flexible. We obtained that very different methods, or even the same methods but with different settings, were able to provide quite similar landscapes. However, this changed a lot when the complexity of the system increased. In the first case, we have a relatively large and flexible molecule like the one we could find in pharma. In the other case, we have a multi-component system. And for these two cases, the overlap of the landscape between different groups was particularly low. There was, however, an exception. Two groups generate very similar landscape throughout all the different systems. This is particularly encouraging because these two groups were also the ones that found the most experimental structures. So there were something in their methodology that allowed them to exclude not plausible structure from the beginning.
Who were they, if you're allowed to say?
You can see the papers. One last thing to look at is the case of polytypism. We had some structure within the generative structure that were kind of hard to identify similarities between them because given the fact that the differences were relatively low, most of the methods that we use, which are automatic methods, basically failed in the beginning to find differences between them. This was the case for molecule 29, which was Z prime equals 3 structure, so it was particularly difficult for CSP methods. And what we found was that the experimental structure on the left was found by a single group, while another group actually found one structure that was extremely similar, meaning they had 5 layers out of 6 that was in the same position. If we want to use crystal packing similarity and identify effectively differences between these two structures, we need to move to very large molecular shells. So and that's obviously increases the computational cost in comparing this kind of structure. So we are trying to find alternatives to better identify these cases. So in conclusion, CSP methods produces very large amounts of crystal structure, so we need efficient approaches to assess the similarity between crystal structure generated to remove duplicates and find the matches with experiments. We have done a lot of improvement to crystal packings, similarity, and when we are considering structure that have been obtained at different condition, we also need to take care of possible thermal expansion in that case. About the PDD instead, again, it was a kind of crude method, but it was very effective, extremely fast, and allowed us in a reasonable time to perform more than 200 million comparison of the structure. So it was a really effective way of using it. So for knowledges, there are obviously all the group that developed the crystal structure similarity algorithms, crystal packing similarity in here, especially Jason Cole and Murray work a lot on this. The group of Erin Johnson and Alex Mayo for the variable cell powder difference, and the PDD code by Diane Wilderson and Vitaly Kurlin. There is all the blind test team that worked with all the participants in retrieving the structure, having contact with them, and reply every question. And obviously all the people that participated in the blind test, which more than 150 researchers. And one final thing, we have some webinars and events in the next month, so please go to the CCDC website to check that. Thank you.
Great. Thanks, Nicholas. Any questions or comments? Line, we don't have anything. Anyone here? Okay, good. Otherwise, let's leave that for the pub afterwards because we're a bit over time anyway.
Oh, yeah.
So let's thank all the speakers again. Thanks a lot, everyone. Okay, so we will locally then go to the Pen and Arms for those who have a bit of time. Online, please stay. We'll put people to breakout rooms to have a chat as well. I wish you a very Merry Christmas as well, and see you all in the new year then. Thanks a lot, everyone.